So we'll talk about industry. We already indicated that this model can be used not only for residential building, but also in industrial production. I'll be showing other methods of AI. It's purely data-based. What we saw before, we could refer to it as a physical model, where you address physics. And the second option will be purely data-based. In the buildings, we could just use beam and heating information. We wouldn't need the actual building and the data. It's more advantageous because you can validate your models, but it's not necessary. When we have good quality information, we can calculate all the data ourselves, but with the industrial, it's purely data-driven, and these are data processing methods. So it's not like with robotics that simulation, everything worked, but when it came to practice, other factors were discovered that impacted the result at the end of the day. With buildings, you need to fine-tune, but it's much easier than robotics. So let's move on to your second presentation. The second presentation follows up to what Radek Fiala mentioned before, and these are methods for the energy efficiency or energy demand of production processes. There are two steps. The first one is to identify inefficiencies, then be able to identify the inefficiencies and the reasons. And the next step is to predict the actual consumption for the next day. So at 6 p.m., say, okay, this is our production plan. What will be the consumption for the next day? These are two different categories, and therefore we have two different approaches. Historical data for training or for the preparation of the models, they are the same, but the approach and the outputs, this is different. I'll start with identification of inefficiencies. The key requirement is to be able to explain it. So here you have data. It's not important what part of the plant is concerned. For this case, we need to know that what is in red is actual energy consumption and blue is a reference value. In this case, it's the number of square meters of a product. So I have consumption, I have reference value, and I try to train the model that will find inefficiencies. The first thing to do after clearing the data is to do a correlation. In this case, the correlation value is 0.8, which is not bad, but maybe it could be better. What it's telling us is that the consumption doesn't only depend on the number of square meters produced, but there is something missing. So we would need to add further reference vectors to improve the data. What you saw before was a timeline, so consumption and production as a function of time. And this is a chart in which you do a regression. It's a method we selected to identify the inefficiencies. So on the x-axis, you have production rates in kilograms. Where they use square meters or kilograms, so I didn't say it correctly, it's in kilograms, and then energy consumption in kilowatt hours. When you take a look at the chart, you can read a lot from it. For example, 1,000 kilograms can be produced with 40 kilowatt hours, but 500 at 10. So you need to be careful with the data. You need to do a lot of things with them, as Radek mentioned already. As I said, what we need for inefficiencies is a model that is explainable, because when you approach the client and say you have a 20% inefficiency, in what? I don't know, AI told me. So nobody will talk to you anymore. So you need a model that is able to interpret it in a way. So those of you who are familiar with linear regression, it's this linear regression of formula. So you have energy, it's lighting, various things which you are unable to quantify. Then this part depends on the number of products used. So beta coefficient tells you how much energy you need per item, or per kilogram, or per square meter. So it should be linear. In most cases, it's linear. So 1 kilowatt costs so much, 100 kilograms costs 100 times more. Then we have weather, time, data, whether it was a public holiday, whether it was a Monday, what shift, etc. And the last one of the most important things, I'll be coming back to it, it's a residual. It's something you're unable to determine, and many times it determines the accuracy of the model. It's a residual, it's an error. Why did we pick regression, and especially quantile regression? Regression is robust to outliers. It's more suitable for industrial energy data. It can handle skewed data. And with a quantile regression, you can handle the data based on the quantile you pick. When you pick the quantile 10, you say that only 10% of your data are below the regression curve, and you say, okay, I'm being very strict, everything above the curve, it's an error and inefficiency. Therefore, we picked quantile regression. My colleague mathematician wrote down the equation of the quantile regression. What's most important here is this line and this word, that it's an optimization problem. That mathematical optimization, when you ask a mathematician what optimization is, you are looking for a minimum of a function. And with a quantile regression, you're looking for the individual parameters to find the minimum of the function you're addressing. And that's the entire principle of this linear regression. Linear regression is a quantile regression with a quantile 0.5. So each model can be evaluated with certain metrics. There are lots of them. You can pick various ones. You can pick your own if it suits you. One such ideal for me as an engineer is in percent. So how this model is inaccurate. I can imagine it easily, and those others need to be linked with maximums and minimums of data. I like MAPE the most because it will tell me the accuracy of the model in percent. So we took our original data and we created a model. So red is actual consumption, yellow or orange is the model that describes the behavior for a quantile 0.5. We need to say this because here the model estimates above the actual consumption. So they were very energy efficient here, which is not necessarily true. But if we put quantile 10, we're somewhere here. And then the question is which one is correct. We leave it up to the user. We create a tool, and the user can do what they want with it. So we have these metrics here, MAPE 19.2%. So the model is not quite accurate, but there is one thing that I will stop by. Unfortunately, it's not visible here. I was talking about the error. This epsilon at the end, those residues. And there is a philosophical question now that we're addressing. We're able, because it's an optimization task, we're able, in many cases, to really minimize the epsilon. So in many cases, we are able to come up with a model that will copy the actual consumption. But in this case, it's counterproductive. It's of no use to us because we will teach the model using inefficiencies and we will not be able to identify them. So what we need to do, and we are arguing about this, how strict we should be to the operator and tell them where they should put the best production. If we took an example which doesn't correspond to reality, and if we tell red is the actual consumption, there are no external parameters, I would ask, please tell me how come that here you've produced 10 kilowatt hours per kilogram of product, and here here it's 50. We could say all this is an inefficiency. On the other hand, it's not quite true. So we can argue about this, and we've been addressing this issue for quite a long time, and we'll see where we'll end up. So in this case, the goal is not to get a totally accurate model, because with this, we wouldn't be able to identify inefficiencies. The goal is to find an area in those data where the production efficiency was achieved and say that all the rest was inefficiency, and this is work in progress. Prediction. Here, on the other hand, we need to train a very accurate predictive model that will be able to predict future consumption one day ahead. It's a holy grail a bit, because the same methods can also be applied to predict spot prices. They can be used for different things. And all the community, because the colleagues before they joined the InnovAIte project, they were working on spot price predictions, and they have the algorithm knowledge and the method knowledge from there, and they are applying them now. So it's a kind of a holy grail. And the state of the art, the people dressing it, are on the same starting position. They're trying out various new models, but the accuracy for one day, it can be predicted. As for the spot price of electricity can be predicted quite accurately, plus minus 2%. Then for 3 days, it's not accurate at all. As for the models that can be used, there are lots of them. We've implemented a lot of them because we're dealing with timelines. When my colleague took the data that we got, he tried most of the methods, and the best results were given by recurrent neural networks. So for this specific case, we're using the recurrent neural networks. So it's a sequence-to-sequence model. On input, you have a timeline. In training, it's actual production, and on the output, it's actual consumption. This is for training, and for inference, I'll tell it because it's important. For inference, there is planned production on the input, and there should be consumption predicted by the model. Again, we're using the same data sets. Red is energy consumption. Blue is the number of kilograms of product produced. So the training worked in the way that we had data for the period of 1 year. My colleague picked 11 months to train the recurrent neural network, and we used the last month for testing. So we trained the neural network, and in the last month we had 30 days to test the accuracy of predictions by the neural network. For inference, the recurrent neural network needs the cause of the reference value for the last 72 hours. So you can see that this is the actual consumption for the 72 hours and the prediction for the next day. So blue is actual consumption, red is predicted consumption, and these are different days. I just gave you an example. Sometimes it gives accurate predictions, sometimes it underpredicts. So our prediction is much less than actual data. When we started thinking further, okay, our model is trained and tested, what about inference then? We discovered one interesting thing. We talked to the people from the company and they said, well, our plan looks like this. It's a constant. They have a plan for the entire day, 2 or 3 days, and they expect that the production would be continuous, so that they produce 24 tons in 24 hours. So they should produce 1 ton of product per hour. That's the plan. But the reference that we used to train the neural network was actual production, not planned production. And suddenly we found that there was a problem, because the plan looks completely different than what we trained the neural network on. So now we are thinking how to design a transformation function that will tell us what is the relationship of the plan to actual production. So we are now we should do a side step or a step back and start addressing the connection between planned and actual production. And when we have this, we can continue in improving our model. We will get more data to make the model more accurate. So much to where we got in the part of trying to identify inefficiencies in production, and where we got in predicting actual consumption. Okay, so if this is everything, thank you, Mr. Tomáš Karásek, IT for Innovations. Mr. Karásek, because we're a bit behind our time schedule, I would propose, if our guests have any additional questions on their second presentation, we'll have one more presentation to conclude today, but then you can enjoy your time over the coffee break and maybe approach Tomáš Karásek from IT for Innovations and talk to him in person.